Thank you very much for joining us today. My name is Todd Rimmer. I'm a Director of Software Architecture with the Intel Connectivity Group. I'm going to talk to you a little bit about what's going on in high-performance networking and the relevance of Ethernet to that. All right, so let me just first clarify what is high-performance networking. And so certainly it starts with HPC, high-performance computing and building clusters, but it's expanded a lot more beyond that. So there's a wide range of workloads today that require high bandwidth and reliable connectivities with good latency. Many people start with HPC as their first thing they think of when this topic comes about, but there's a lot of activity in artificial intelligence and machine learning, other forms of accelerated computing, and there's even some workloads that are involving databases and storage that can take advantage of these same kinds of network technologies. Now, one of the most revolutionary things that have been going on in the networking industry over the past few years is the transition to the cloud. And so it's important that products developed to support high-performance networking are able to support both on-prem deployments, which is where classic clusters have been used in the last 10, 20 years, ever since Beowulf began, and cloud deployments, which is where a lot of the growth is occurring and where there's a lot of interest in being able to run these workloads, as well as environments where you can run the same workload either on-prem one day and on the cloud in the next. And so it's very important when looking at these kinds of solutions to take an end-to-end approach and think about all the components involved in the solution and make sure that the ecosystem and the piece of software come together to permit these workloads. So, everybody always asks, where does Ethernet fit in the picture of high-performance networking? And so, Ethernet's been in the forefront of high-performance networking ever since the days of clustering in the late 1990s when Beowulf demonstrated the importance of parallel computing and clusters. And so it's still a very significant portion of the overall HPC landscape, although it doesn't always get the publicity that some of the top systems achieve. But Ethernet has been changing a lot in the last 5 to 10 years, driven by the cloud and its requirements. And so the cloud has really transitioned the definition of what is Ethernet and what's it capable of through their own requirements to build hyperscale data centers with hundreds of thousands or millions of servers connected together in warehouse-sized computing and solve key problems like building large-scale class topologies, getting efficient routing, getting efficient congestion handling mechanisms, optimizing for tail latency with a wide range of applications, and wanting high radix switches and high performance capabilities. And as they transition towards more and more microservices, their needs in the area of high performance networking continue to grow, and these needs are very similar to the needs of classic high-performance computing and AI training. So we see Ethernet as continuing to grow in this space and continuing to gain adoption and continuing to expand its capabilities. So within the portfolio, Intel, is a full capability network provider company. We've provided a set of software that enables the use of our Ethernet NICs and our Tofino switches to efficiently run these workloads in a competitive and performant manner. Our Ethernet 800 series of NICs can give you RDMA capabilities via Rocky at 100 gigabit Ethernet and fit into modern servers. And there's an ongoing roadmap of NICs planned. And then, of course, we've talked a little bit in the last session with Peter about the Tofino switches. These are a very competitive Ethernet switch, giving you 6 terabit, 64 port, 100 gig switching in Tofino, and Tofino 2 giving you 12.8 terabit per second in a variety of port configurations. And so this is a very competitive, very interesting portfolio of devices which we can then deploy to solve and run workloads in the high performance networking arena. So this cartoon is a representation of a typical high performance networking cluster. The focus of the discussion is often around the compute nodes. There may be hundreds or even thousands of compute nodes in one of these clusters, and then they're assembled traditionally with a class type fat tree topology with a mixture of director or edge switches from a variety of configurations. And then there's surrounding set of service nodes, file systems for storage, other services, and some management capabilities. And this picture is actually very similar to how the cloud deploys their environments, with the compute nodes typically being the environments that customers directly rent to run their applications, and then a variety of other services surrounding them. So there's a lot of good alignment to what traditional HPC and AI training have needed. And so to fit in this environment, what we're producing is an overlay set of software we refer to as the Ethernet Fabric suite. And so this can be run on all the hosts in the cluster. It gives you a traditional set of high performance computing and AI training software stacks and tools and capabilities. And then surrounding that, you can use other software from Intel's portfolio, such as our Intel MPI, our math libraries, various compilers, tools for analyzing Tofino switches like Deep Insight, etc., and take advantage of a variety of third-party software that we've designed our components and hardware and software to fit naturally within. And then on the control plane, there's a strong ecosystem already established for clustering. There's a variety of products out there from other vendors and in the open source community for managing servers and server provisioning and launching jobs, scheduling them and tracking them. And so we designed this to fit naturally within that existing ecosystem, so customers can take advantage of tools and features that they're familiar with. And what we're doing is we're augmenting some of these capabilities by bringing to it additional tools. In this first incarnation, we've got a set of deployment verification tools that help you to verify the cluster was installed in a performant manner, that various cables and things are in place and functioning well, and that you have the configuration you want, and you've followed good recipes for getting the best performance out of the cluster. So this is a little bit more detailed view of the host stack, kind of with a focus on the compute side at the heart of this. And so what we've done is we've brought to market a port of our existing OmniPath and TrueScale implementations for high performance networking. And so we've taken this third generation of our performance scaled messaging protocols and software, and we've ported that to run on standard Rocky, and hence it can run on our 8000 series of NICs as well as future NICs that we'll be providing. And so this fits naturally within a traditional high performance networking stack. And so we can run this as a LibFabric provider. All of the popular MPIs and other middlewares already support LibFabric, so they're instantly supported, as well as all of the existing applications that support and run over any of those MPIs. The E800 series has strong capabilities for the verbs set of protocols and APIs, and so existing file systems that have been optimized for other RDMA networks also instantly run without any effort on this environment. And so by taking advantage of standards, we can bring to bear the maturity of almost 20 years of tuning and optimization and features that have been built into this performance scaled messaging software, and bring it to the Ethernet portfolio and allow it to work with our NICs and with our switches ideally, but it works actually with anybody's switches because it works with standard Ethernet protocols. So the first thing anybody asks about in high performance networking is, what is your performance? A very logical question. E800 with this software on it, and what you're seeing here is a a comparison against InfiniBand, the 100 gigabit aka EDR solutions of InfiniBand. And so what we see here is that for most of the applications, we're within 3 to 5% of the performance. There's some that this software performs notably better than InfiniBand, and represents a reasonable cross-section of different types of high-performance computing applications. All right, so what are the other key metrics that people like to look at for evaluating high performance networks is latency. Now, the challenge here is latency in the real world is rather challenging to measure, and a lot of vendors have driven people to focus on the easiest thing to measure, which is 2-node latency. Just hook up a couple of nodes, you run one process per node, most of the CPU is idle, and let's see what the latency looks like. And that's maybe somewhat interesting, but it's analogous to just revving the car in the parking lot. That's not a very good test drive of how the network is going to perform in the real world. And so what we've done here is we've compared InfiniBand with the E800 Ethernet NICs using the HPC random ordered ring latency. So HPCC is a high performance computing set of benchmarks. It's a public set of benchmarks available. And this particular test represents a more realistic pattern where the nodes vary who they're talking to. It can be run on more than 2 nodes. It can have multiple processes per node. And so this represents a more realistic environment where the NIC has to deal with different conversations with different nodes, changing traffic patterns, etc. And this is very revealing because we can see at the left of the leftmost chart that for the 2-node environment, you can reproduce those advertised hero metrics that people see. But as you scale up to as few as 8 or 16 nodes, with InfiniBand, we see a notable change in the latency that occurs. And this is because the InfiniBand's been tuned for a lot of advanced strategies that turn themselves off as they scale to a few nodes. And so it's not really representative of what you see. Now, what we see on the PSM alternative using Intel's high performance networking solution in blue is that the latency is very flat and level. So you get very consistent latency. That 2-node latency you run that you do is actually very representative of what you'll see at scale. And in the rightmost chart, we've taken that same solution and scaled it as high as 112 nodes. And you see that the latency continues to remain very consistent and very flat. And this is really what's the most important thing for the real world applications is what kind of performance do you get, with a real traffic pattern, with a lot of variety to it, with scale, which is the way you're going to really run your applications and is why you're buying a cluster. Nobody buys a cluster to run 2-node applications. They want to run 10, 50, 100 node or more. So the other part of the equation is cost, and this is another factor where cloud has been changing the nature of the game. The cloud providers have been, driving all of the networking providers to find ways to drive cost out of the products while retaining performance, while having high radix, while having the flexibility. And so this is driven to higher radixes and lower cost ways of delivering the hardware and the software to the end users. And so all the end users benefit from this. And a lot of the cloud focus has been around Ethernet. And so those advantages are being driven into the Ethernet solutions. And here we see a comparison at a variety of scaling points up to 100 nodes of the cost of the networking portion of a cluster, the NICs, the cables, and the switches between InfiniBand 100 gig and the Intel 100 gig solution. And what you're seeing is you're saving anywhere from 25 to 50% in the cost over equivalent InfiniBand solution. Now, what this translates to for most end users work with some kind of a fixed budget. They identify from their company how much they can spend, and then they want to build the best performing cluster they can purchase for those dollars. And so by reducing the cost of the networking, this usually translates into being able to afford a bigger cluster with more servers, which, it always gives you more performance than a smaller cluster and more potential to run more jobs. And so what this turns into when you combine it with the previous chart is a lower total cost of ownership and the ability to actually get bigger and better performance clusters for the same dollars, because you're going to get the same performance or an equal node count job, but you can afford more nodes and hence get more overall performance. So in summary, what we see is that Ethernet is already a very significant part of the HPC and the AI training landscape. Its growth is expanding to larger clusters. It's continuing to get advanced features to deliver application performance that continues to improve it with each generation. It's extremely competitive with InfiniBand and other proprietary solutions that are out there. So what we're bringing to market is the third generation of a very proven set of software that makes notable improvement in the performance as compared to what you would have seen in Ethernet a couple of years ago without this software and without some of the advanced capabilities that are in the current hardware products. And so this helps derive, better application performance, better cost structure, and it ends up being on a network that virtually every sysadmin on the planet is familiar with the ability to configure and operate. There's certainly a wealth of Ethernet experience in the industry, and any sysadmin worth their salt has been trained in how to operate Ethernet, which makes it much easier to use than the proprietary solutions such as InfiniBand, where there's only a small number of sysadmins that really understand how to operate those environments.
So speaking of proprietary and cost savings, one thing I've noticed a bit of a trend on Intel's NICs happening is vendor-branded optics. And I know that's one of the benefits of Ethernet, right, is that it's very standards-based, whereas InfiniBand, like you mentioned, is more proprietary. Kind of curious, I don't know about the 800 series as much, but, is that a direction Intel's wanting to keep taking? Because that seems to be a bit, contradictory to, trying to be less proprietary and trying to save money, is locking into specific pluggables. And it's also difficult with things like active opticals and DACs. I mean, I can't buy maybe you want to sell me an Intel switch, but, I can't buy a switch that has Intel on the other side, right? So I already have to go and get custom branded cables, so.
So there's a variety, there's an ever-growing set of choices of cards designed with the E800 series ASICs on it. And so a variety of OEMs are offering, different cabling solutions. There's certainly a wealth of ecosystem out there. Intel, does have its own silicon photonics cabling solutions, but our focus is to make sure that the ecosystem can work well with our products, and then the customers that see the value or differentiation in some of our solutions, like our silicon photonics cables, can have that choice. But we're not trying to lock people into that particular solution, because we do have all of our cards, or a lot of our cards have standard form factors and connectors that'll work with other vendors' cables.
I had a quick question in regards to performance for some other aspects around the card, maybe specifically around PTP, around precision time protocol. Do you guys have any performance numbers around how you guys deal with like real-time precision and what you deal with in high congestion networks? Because there's some interesting research papers talking about the fact that PTP doesn't perform particularly well in high congestion, larger networks versus like smaller topology configurations and in some larger multicast configurations. So I was sort of curious what you guys have in terms of capabilities there.
I don't have that data with me today, so that might be an interesting topic. If you're like, we could set up a discussion after the field day sessions, and I could get you connected to the PTP experts. There's a variety of things going on in this space, and one of the exciting things that we alluded to in the previous session is the programmable switches. And so the really cool thing here is you can design your own protocols. You can design all kinds of specialized packet processing and packet inspection in P4, which means that you could start enhancing how congestion management mechanisms work in clusters. There's papers out there. We've done some preliminary work on things like how to offload collective operations. There's a paper called Switch ML describing how that was done in conjunction with Baidu. And so there's a lot of opportunities here after you've deployed the cluster to take advantage of these programmable elements and actually introduce new protocols and new features without changing the silicon.
It's kind of on the topic of what Ed was saying about precision time protocol. Is it possible to turn off some of the error correction in these NICs, which also can impact PTP? And is it also possible to enable I forget the exact term, but I believe it's like the timestamp pass-throughs or the hardware timestamping of the switches with PTP pass-through and things like that on your NICs? Because I know within an HPC environment, that precision timing is real important.
Right. So, it's up to the software load you have, whether you've even turned on PTP or not. A number of the HPC environments try to limit the amount of extraneous traffic on their network to get the lowest latency. So by default, a lot of times people will configure their OS to not be doing that, or doing it very infrequently, or have their control plane doing that kind of stuff very infrequently. Now, one of the things that I didn't have time in this slot to cover is we've got a feature for the Tofino switches, a piece of software we call Deep Insight. And Deep Insight allows us to look into the network itself much more detailed than we've been able to ever in the past. And so it lets you really analyze the latency observed for individual flows, the performance that you're seeing, where the bottlenecks and queuing points are in the network, which switches have the deepest queues, and for what kind of traffic. And it's a very powerful package that's also going to be, solve many of those same problems that people might have been doing with other mechanisms in the past. And that too takes advantage of the P4 programmability of the switch, its ability to do deeper packet inspection, and then to mimic the relevant portions of that off to a data analytics platform. So there's a lot of cool things that are going to come currently and in the future through the programmability with P4.
Yeah, I sort of understand the flexibility that you get with P4. I just don't think P4 is in the landscape of where most folks are going to fit in terms of doing something with, in terms of trying to tune this. I think there's an expectation that the vendors or manufacturers that we would be buying equipment from would be doing that work for it. So I don't know what your expectations are, right, Todd, but I doubt you're going to look at end users, right, even enterprise end users, as really going in and saying, like, we're going to dive in on P4 and bypass what our vendors are saying. And by the way, we'll void our warranty as part of the software process too, right? I mean, it's...
Well, but there's a way of looking at this differently in that, and this has kind of been driven also how the cloud wants to look at things. The software has a timeline of, months, weeks, sometimes days to make changes. Hardware, you come up with a new feature idea, someone agrees to do it. It's 2 or 3 years before you get a new ASIC with that feature. Yeah. And so what this does is really accelerate that time. So if an end user is not inclined to do some of these things themselves, they can bring them to a third party. They can bring them to Intel, and it's feasible to do these things without having to spin the ASIC. It's, we can take advantage of this programmability and deliver these features. That was the example, the nature of some of the work in that Switch ML paper. It was collaborative research with a cloud provider that wanted to try to optimize AI training workloads and wanted to take advantage of P4. And so we're seeing, certainly in the cloud providers, we're seeing some of the the traditional HPC customers in the space, like the government and the universities that want to take on, trying these kinds of things themselves and adding features and innovating, and in some cases doing things very specific to their own workloads that would never justify, driving a hardware vendor to add a feature to an ASIC. But here they experiment with it. But I agree, there's going to be a set of people that just want a a shrink wrap solution, and they don't want to quote open the hood and look at what's going on and change it. But that that capability still allows them to drive requirements into the ecosystem so that some other vendor or Intel can add those features for them onto their existing hardware without replacing their hardware.
No, I mean, I understand the advantage of being able to do like some sort of RFP input requirements. That's the P4 is a set that fits in there, but I find it unlikely, probably even in the Fortune 1000, that you're going to find a lot of shops that are going to be willing to tackle this on their own accord. And maybe maybe Chris Cummings and a few others are the exception given those shops that they're working out. But I see that as, I know it's sort of the default answer in terms of like what Intel is saying around, say, hey, we got this capability here. But I think it's almost a level of abstraction too far away. It's like totally cool to know about. But for me to go through and grind through P4 to be able to figure out how to, get most of this to work would probably be a lifetime of effort, at least for me. Not that I'm saying I'm a crappy network engineer. I just think that it's sort of out of the realm of domain of where most folks would fit that would want to be able to utilize the product versus, from an operator basis versus, where it fits in terms of this side. Just an observation. I'm not saying it's good, bad, or different. I think what P4 has done is pretty remarkable and really incredible what you guys have done on the silicon side. And then obviously being able to push that into the the pure Ethernet on the chip side for being able to provide that for Ethernet cards or for LAN on motherboard eventually, that would be really cool. But I don't know, maybe I'm the only one that thinks that way.
Right. Well, I think there's going to be a variety of skill sets out there. The P4 is not that much harder to program than say C, and there's certainly a wealth of engineers that they've been able to pick up C. And I see this as kind of the beginning of a wave, right? If you went back, the first generation computers were hardwired, and everybody, there were very few people that could program computers once the first generation of programmable computers came around, right? And then, that's transitioned a lot. There's been multiple steps and generations between now. This is, the beginning of a new world of programmable networks, but we're leveraging many of the characteristics of programmability that we've seen in the past for processors. So, languages like P4 have a semblance of very similar to C in their syntax. The capabilities are built into advanced compilers, so they don't have to think as much about the details of how the hardware functions. You're no longer, quote, programming an assembly language. You're programming in a high-level language. But I agree there's going to be, a certain tier of the environment that, people are willing to, certain class of customer that will be willing to do that program. But I think we'll see that grow over time as people become more familiar with the languages and want to try things on their own. But it'll take a little time. But there's definitely an ecosystem of people out there already that are experts and can do consulting and such to help help average end users create P4 programs for unique requirements.
I think I'll pile onto that. I don't know that the language is the hard part when it comes to P4. It's the pipelines and understanding pipelines. I think that's the hard part. It's a big difference and change of mindset. It's I don't think it's quite as easy as saying it's just like C, but a little easier. There's a lot more to it than that.
Yeah, well, there are classes. I mean, I took a P4 class about a year or so ago. The Barefoot Academy has a series of classes. In a course of a couple of days, having never seen P4 before, we were creating useful algorithms and changes to existing algorithms in P4, running them on real silicon. So, I think if you have a person that's reasonably talented in programming something like C or similar languages, they'll pick it up pretty quick. And there's certainly different tiers of programming skills out there and different degrees of motivation to learn a new technology. But it's definitely much easier than trying to pick up writing machine code for a modern processor or something like that, or how you used to have to program switch pipelines a few years ago, where you didn't have these high-level languages and you had to be intimately aware of every bit and byte in the switch hardware. So P4 has changed that dynamic, and I think it's going to bring. It's not like your average app programmer will be writing in P4, but I think there's going to be a certain class of programmers that have historically done systems type programming. They're now going to be enabled to do things that they couldn't really do a few years ago. So, but there'll be an interesting ecosystem occurring around it.